Right. Hello. Thanks for coming here. Okay, clicker works. So I'm going to try to today I'm going to try to tell you about how asyncio works. You may have seen introductory talks and a lot of stuff. You need to take a bit of a leap of faith to believe how it works. Today I'm going to try to explain how it actually does. So quick recap. I hope you have all been at Rodrigo's talk so that everything is familiar. But asyncio is this new framework in Python 3.3 or higher. There's a backport for Python 2.6 and higher called Trollius, so you can even play with it. The PEP is 3156 for those who want to check it out. And this framework was created as a modern I/O framework using new language features like yield from, which we will see in a bit. So a bit of an advisory. I'm going to dive into the internal parts of the code. The fact that they are internal, it means you need to know about them, but never use them like that. So just know about them. I have basically code from the asyncio framework, which we're going to step through. And some slides have a tag saying simplified. That tag means I reduced the code. Usually I remove some error checking so that it fits in one slide or makes it easier for me to explain. But I didn't modify how it actually behaves. So first, the architecture. So for me, there are three main things in asyncio, which is the event loop. Then we got the coroutines, features, and tasks, which someone may have told you about. And that's where we're going to spend most of the time. And then we have transports, protocols, and streams, which we're going to not dive into today. So that's the homework for you, looking into transports and protocols. Basically, they are built on top of the rest. So if you get the first two, the other two are sort of a byproduct of those. So let's look at the event loop. The event loop is a very we can simplify it into these circle here. So we need to calculate for how long we poll for I/O, then we actually poll for I/O, and then we run some callbacks. Simple, right? So in asyncio, there is no abstraction for what an event is. We define this entity as an event loop, but there is no event class or anything like that. They are all callbacks in a DQ. And these callbacks can be added there because of time, because of I/O, or because we want to. And then we just need to run these callbacks, and this is why our event loop acts as an scheduler of some sort. So let's look at the first function. This is the simplest way to schedule a callback to be run by our event loop. It's called call soon. So first thing we do is we create this thing called events.handle. It's basically like a callback wrapper. And this thing is what will then run our callback. Then we append it to this ready DQ, and we return it. This handle object has, for example, the cancel method. So we can just take it, and if we don't want this callback to be called, we just can call cancel on it, and then it won't be called. Of course, if it has already been called, well, tough luck. So this is the simplest way to schedule a callback. And this is the quick explanation. Now let's look at how to schedule an event based on time. These are call later or call at. The event loop also holds a heap where timers are stored. When we create this timer here in call at, actually, as you can see, call later is implemented in terms of call at. This timer handle inherits from handle, so it's kind of the same thing, a wrapper for the callback. However, it also knows when the callback is due. And it has the comparison methods required for the timers to be sorted by due time in this heap. When we do the heap push, they will be sorted by closest due time. And then this way we can, let's say, take the first entry in our heap, and that will be the timeout we need to wait for because it's the first timer. So how do we run our callbacks then? This is the main meat of the event loop when it deals with running the callbacks. So what it does is runs everything that is stored in the DQ. Now, to some of you, you may sort of look at this and think, well, that's not very Pythonic, is it? Because we're taking the length and then we iterate over it. The reason for doing it this way is twofold. First of all, we want to run the callbacks that are in the DQ right now. If one of our callbacks schedules another one, this newly added callback will need to wait. We don't execute it now. We will do it in the next iteration. It will be in the queue, so no problem. We will do it. but just not right now. And iterating a DQ like this is thread safe. So we will see a bit later how we can schedule a callback from a different thread. And then we will modify this DQ from another thread, which means we need to be careful about how we handle this queue of ours. And this is a way to iterate, because this is the only place where the DQ is iterate. Everywhere we append, and here we just iterate over. So this is the only place where we do it, which means it's safe for us to do it this way. So we said we handle time and we handle I/O. Now, on Unix systems, there are a lot of different ways to do I/O. So we have select, poll, epoll, KQ, dev ports, take your pick. And they're all different and work different. Windows is a totally different beast. The model is different. Basically, on Unix, the paradigm is readiness. So please let me know when you're ready to read. And on Windows, it's basically read and call this callback when you're done. It's sort of completion-based. Once you're done, tell me. And APIs are provided for both in our event loop. So we have two sets, the readiness style and the completion style. So readiness style, we call add reader, add writer, or remove reader, remove writer, which are based on file descriptors. So tell me when this file descriptor is readable or writable. And on the other APIs, take socket objects. So please send data on this socket or receive data from this socket. So these are completion-based. They won't tell us when it's ready. They will tell us when it's done. Now, there's a new module in Python 3.4 to abstract us at least from the selectors nonsense that each Unix system has a different one. It's called the selectors module. And this module implements all of them and takes the best pick for the current platform. So if you find yourself in the need for a very, very thin event loop that only has to do with Unix, you can use that one. Of course, what do we do on Windows? Everyone loves to hate Windows, but the reality is it's a thing that kind of works and it's deployed a lot. So now selectors works on Windows. However, it can only use select, which by default is limited to 64 file descriptors, which is kind of not a lot. You can override that to be 1024, but that will not drive you very far. So the way to do I/O on Windows is IOCP. IOCP is I/O completion ports, and asyncio has a binary module implementing this thing basically for the event loop that runs on Windows. On Unix, it's built on top of the selectors module. So let's see how add reader works in our case. So as always, we create a new handle to wrap the callback we want. And then we basically operate on this idea of a key. This is how the selectors module works. So the key basically is the representation of a file descriptors, the events we're interested in, and some arbitrary data. In this case, our arbitrary data is the read and write handles. So we can only have one reader and one writer per file descriptor. Otherwise, imagine you would like say, oh, this socket is readable to two different entities, and which of them sort of reads faster. It would be like racy. So if there is already something, if there's already a key, we modify. That means if there's already a key, it means there was already a reader or a writer. So if there was already a reader, we cancel it and we insert the new one. Or if there was a writer, we add the new reader, and that's it. So eventually, this handle will be called, our callback will be called, and then the rest of the loop can continue to work, in the sense that probably what happened is that you want to read some data from the socket. You said, okay, well, I want to start reading from here. So let me know when there's some data so I can do the actual reading. Now, how do we do the actual polling for I/O? We said we need to calculate the timeout, then block, and then run some callbacks. So this is basically the order of things that happen in the asyncio event loop, like the sequence of actions. So first, we calculate the timeout. That means for how long will we block for I/O? Then we block for I/O. This could be a 0 timeout. It could be an infinite timeout if there is nothing but the TCP server and we're waiting for connections, whatever. Then we process the I/O events once we come back from blocking. That means we add callbacks to our ready queue, remember? Then we process the timers. So timers may have expired by now because we were blocked for a bit. So maybe a timer or two are due. So we take them out from the scheduled heap and we add them to the ready queue. And finally, as we saw before, we process our ready queue. So how does this look like? First, we start with timeout none, which is basically if nothing modifies the timeout variable, the timeout will be infinite. Timeout none means timeout until there is activity in any of the sockets being monitored. Then if we have some callbacks from our previous run, it means some other callback was executed, we poll for 0 seconds. This means that we will not block for I/O. Well, technically we will, but only for 0 seconds, which is close to nothing. And that way we can run our callbacks without waiting. Then, if there is some scheduled timer, we will compute the nearest timeout, and then we will use that as the time for us to block. Then we use the selector API to block for I/O, is this selector.select. And this uses the best one. It doesn't use select. It could use epoll or KQ, whatever. Now, what we get back is a list of file descriptor and event tuples. And then this function here, process events, will basically take this information and add the handle events to our ready queue, if they're ready for reading or writing or both, whatever. And finally, because we are back from polling, we take our due timers, we take them out of the heap, and we add them to our ready queue. So we now have a queue full of callbacks. Some of them are because of I/O, some of them are because of call soon or whatever, and some others are because of our timers. And here, the missing part is that code we saw before to iterate the queue in this thread-safe way and execute all the callbacks. So I said I would explain this thing with threading, and it's this function called soon thread-safe. So this is, I think, the only thread-safe function in the whole asyncio. And the only thing it does is it schedules a callback to be run by the event loop, but it does it from another thread. So how does it actually work? As you can see, it's that simple. So the first thing we do is we create a handle, and we call soon with it, which means that we added it to the ready queue. However, because we're in a different thread, we don't know on what state the loop is. The loop might be on an infinite poll. So we need to wake it up. The way we wake it up is by calling this write to self function. And this is implemented in the following way. There is a socket pair, so a pair of sockets that are connected with each other, and the read end is added to the loop selector. So there's always one file descriptor, this self socket thing. And then what we do is from a different thread, we write on the right end of that socket. So then the read end becomes readable and wakes up the event loop, says, hey, this socket has activity, process the events. That's how you wake up the event loop when you are in another thread. So now let's dive into the next big thing, which is where we're going to spend most of our time, coroutines, futures, and tasks. This is sort of the hairy part of asyncio. So it's a bit hard to explain everything without knowing everything first. So we'll take a leap of faith at some point, and then we'll come back. If you get lost at some point, don't worry, because as the man said, you can only connect the dots in the future. So you'll know enough. So what are coroutines? Coroutines are, there's nothing special about them in the asyncio terms. So they're just plain coroutines, like in Python, generator functions that receive a value. We annotate them with asyncio.coroutine decorator. There's no need to do it, but there's this convention. So if I look at your code and I see dev whatever, and it has the coroutine decorator, I don't need to continue reading. I know I can do yield from your function, which is the whole idea of asyncio. Let's do these asynchronous tasks and use yield from to wait for one another. We'll see how that works now. So it does also some extra checking in debug mode, but again, not needed, but highly appreciated if you add it. Now, what are futures? Asyncio defines a future class, which is actually not the future from PEP 3148. It's API-wise almost the same, but not quite. And these objects represent a value which doesn't exist yet. So we call a function which calculates Fibonacci of 10,000, and this result will eventually come. But it's not there yet, and this future object is our placeholder. Someone will later set the result, and we will be able to retrieve it Or it might set an exception, and we will also be able to retrieve this exception of ours. We can yield from to wait for the result of a future, or we can use the regular future API, which we'll see in a sec. Now, as I said, this future is not the same future as in concurrent.futures. However, we need to use the concurrent futures package to be able to, for instance, offload some CPU-bound work to a process pool, for instance. asyncio is an I/O framework, so we can only do I/O. Actually, moreover, we can only do network I/O. We can't even do file I/O. Reading a file is blocking as it has ever been. This will not solve it. The only way to do non-blocking file I/O is to put it in a thread. So we need to run some stuff in a thread and wait for it easily. And this is what the concurrent futures package already does. So asyncio provides this wrap future function, which will, if given a concurrent futures future, returns us an asyncio future that we can work with. Sounds a bit weird, but it works very nice. So how does the future work? Basically, somewhere, someone will create a future object. Usually, this is a function that gives a future to you. Then, eventually, some other function somewhere, somebody will call setResult or setException. And this way, the future is now done. It's now finished. We can get the result. And if we want this result, we can either call result on it, or we can yield from, and then we will just wait until somebody says the result, and we will get it. Now, futures, we can also use a callback-based approach. So we can add this add-done callback or remove the done callback. And basically, the function we're passing will be called with the future object, which has just been completed, either with a result or with an exception, and then we can get the result ourselves. And let's, actually, this is the setResult function for the future from asyncio, so let's look over it real quick. When we set the result, apart from some state checking and state setting, we just save it in self_result, right? But then we said that we have these callbacks that could have been scheduled with add-done callback and or remove-done callback if you don't want it anymore. And so we need to resolve those callbacks. So we call this schedule callbacks function. Now this function basically will run those callbacks, but they are not called in place. So we use call soon from the loop so that they are added to the ready queue. As I said, the loop is sort of our scheduler. So every callback, everything is run by the loop. If you want to, if any part of the code needs to call a function later, it's always called with call soon so that it's added to this ready queue and it's called with the rest. Otherwise, we could starve it. Imagine you add 10,000 callbacks and then the loop has no time to do anything else because it's not given time to do so. So let's look at how socket.connect is implemented. This is a blocking function in the standard library, right? So we call socket.connect and that blocks. Now let's see how we can make it non-blocking and how asyncio does it. So the idea is simple. We create a future object. Then we call socket.connect asynchronously, let's say. And then this asynchronous function will eventually resolve our future by setting the result or the exception on it. Now, how do we call socket.connect asynchronously? Well, it's this big-ass thing here. The idea is that first, we always try the blocking function first. The socket is set to non-blocking mode, but regardless, we try. Reason is that sometimes file descriptors are suddenly readable because, well, sorry, in this case, writable, because reasons. So maybe we succeed. And if we succeed, then we're good. But it's possible that we don't, which is the usual case. In that case, we will get blocking I/O error. Now, take a minute to appreciate the beautifulness of blocking I/O error instead of doing OS error and then checking e.errno if it's e would block or all the other aliases. So they did some good job there. So what we do is we add a writer. Remember we saw add reader? Well, here is add writer. And basically we're interested in knowing when this future when this file descriptor is writable, because we need to connect. And when it is, please call socket.connect, so this very same function, but well, with a different Boolean flag here. So when this function is called a second time, registered will be true, and our file descriptor will be ready. So when we call sock.connect again, it will most likely succeed. Let's say it does, so there's no exception, and we set the result. Now, what have we achieved with this? We have returned a future which will be resolved later. Now, the beauty of this is that this function is not a coroutine, so it works in Python 2 and in Python 3, but because it returns a future, we can yield from that future. So we can use this function either in the blocking style with yield from the result of this function, or in the callback style. If you feel like that, you get the result of that function and then call add-on callback and get on with your life and then come back to it when you feel like. So I like to call this the uncallback pattern, because it allows you to uncallback a function that used to get the callback. This asynchronous function becomes synchronous if you do the create a future, set the result from the asynchronous, this pattern. This is the explanation. Now, another functionality that asyncio offers is run the event loop until a future is complete. You can either run the loop forever, or you can run it until something completes. The reason why I want to look at this is because it uses the futures with a callback-based API. So forget about this first line. Imagine it's not there. And we pass a future and we call add-on callback under raise stop error. Under raise stop error is a specific function for the asyncio implementation which raises a special exception that is caught, and then the loop is stopped if this exception happens. So then what we do is we run the loop forever. And then when we return from this function, it can only be because the loop has been stopped. So once the loop has been stopped, we remove the done callback to, we don't want it there. And the future is not done, it means somebody stopped the loop. It didn't stop on its own because the future was done. Imagine the future actually called loop.stop before it ended. That is wrong, and we catch that and raise some runtime error. But the usual case would be that your future finishes, then the done callbacks, as we saw before, when you call set result, callbacks are fired. And when callbacks are fired, one of them is raise stop exception, then stop error is raised, it bubbles up, and it makes the loop stop. And then what we do is we return future.result, which could raise an exception if the future got an exception instead of a result. So this is the other way of using the futures API. This uses the callbacks. If we do yield from future, we use the sort of blocking looking way of doing things. Now, people have told you, Rodrigo have told you before, that you can do yield from a future and wait for its result. But now, how does that magic happen? It's not only the magic of yield from, because yield from is just a keyword that basically iterates over a generator and keeps giving you results, and it gives you the ability to chain them. But the ability to execute the different tasks while not blocking is something asyncio specific, something which is built like this. This iter method is in the future. So when you iterate over a future, this is what happens. Let's assume for a second that the future is finished. So forget about this. Okay, we assert whatever, we return the result. Now remember that in the yield from universe, you can return, when you do in a generator, when you do return, what actually happens is that you, internally, that's converted to raise, stop iteration, and the result, the value of the exception is the result that you returned. So keep that in mind because we will see how that is used later. Now, what if the future is not done yet? Because that's the waiting case. So what we do is we set this blocking flag to true. Now, that blocking flag to true is interesting. Actually, I would say it has a bad name. Think about it this way. we can yield something or we can yield from something. Now, how can we know which of the two you used? Well, when you yield, you don't execute under iter, but when you yield from, you do. So if we are here, it means that our caller did yield from us. So then we say, oh, okay, so you want to wait for me. Then I'll set this flag blocking true. And then I yield myself. Now, who am I yielding to? The only entities that can wait for stuff are tasks, which here's where you need to take a leap of faith. You need to believe that tasks are going to work the way I'm telling you right now, because we haven't seen them yet. So I'll explain later. Now, later is now. What? We're good on time, right? Okay, so let's look at tasks. Tasks is the unit of concurrent work in asyncio. Everything needs to run in a task in order to be, let's say, to run concurrently. You may pass a coroutine to run until complete, but what actually happens is that it's wrapped in a task. If you pass a future, no. Tasks are like deep magic, because it's actually a coroutine that wrapped in a future. So tasks inherit from the future object. So think that anything I said about futures applies to tasks. That's important to remember. And the idea is that a task will iterate the coroutine one step at a time. And when it hits a yielding point, for example, when the coroutine returns a future, the task will say, well, you know what? Well, please call me back when you're finished, because I can't continue. So then this task is done right now. It schedules a callback in the future with the add-done-callback API, and then the objects are kept alive because they're referenced, but this task is done, so it's suspended in a way. We'll see all the code right now. We can use asyncio.async to convert the coroutine to a task. We basically take a coroutine, we say asyncio.async, and that creates a task and schedules its run method. This is a simple example of how we can create two tasks that work concurrently. So this coroutine, the only thing it does is it prints its something, and it sleeps for X amount of time. Right? If you run this, you will see how F1 and F2 are interleaved, because when one task is blocked, let's say, in this yield from asyncio.sleep, well, the other one can run and so on. So they interleave each other. And that's how we, in asyncio, you achieve this concurrency. And now to the hairy part. This is the task's init method. So what it does is we save the coroutine object, and what we do is we schedule a callback, this call soon, to run the step. Step is the function that does one iteration over the coroutine. So it calls next on the coroutine, or, well, depending on how you call the function, we can call send or throw. We'll see now. And we have a number of attributes. The interesting one here, future waiter. So that attribute is going to hold the future we're waiting for. In a single task, we can only wait for one thing. So if you put yield from asyncio.sleep, that's what you wait for. And that we will store there. So this is a step in its simplified way. So what happens here? First of all, we initialize everything. And let's assume that value and exception are none, which is the first time we call this function with no arguments. So what will happen is that we say result equals next core, which means we iterate one step into our coroutine. So we start running our code. Now imagine what we hit right now is yield from whatever, like this socket.connect, right? Which returns a future. Now what will result be? Result will be a future, because that's what the function returned, and we're waiting for it. Okay, so then we hit this block of code here. Now we check if this result is blocking, because here is where we do our check. Because if we reach this place, it means yield from was used, because first we called next. So when we call next, under iter from the future has been called, which means blocking is true now. And then we're here, we set blocking to false, and we call this add-done callback. We use the callback-based API to schedule self-wake up. What self-wake up does is call set result or set exception on the task. So when the future is done, it sets the result in our tasks. Like, okay, this future returned this thing, now you shall continue. And we store this future waiter in a result. So this is how one task actually waits for a future. Let's assume now that that future returned a value. When we call next, we will go in the under iter, and we get a stop iteration because that thing is done now. That coroutine we were running after the future is done, it's finished. And what do we get? Well, we set the result in ourselves to the value of the exception, which is the result. Because in rich coroutines, when we use yield from, doing return result means raise stop iteration result. The other cases are when problems happen. So, for example, if we return nothing, we schedule a next iteration so that we will finish. If there is an error, for instance, if the future returns an error, we will end up calling this function with the exception set to something, and then instead of setting result, we will set the exception, or well, it could also be a base exception like system error or something. So this is how actually the task works internally. Is complex, but it's not magic. So there is an explanation to it. It's a combination between under iter, which, remember, task inherits from future. So whatever I say for future applies to a task. Under iter takes care of setting this blocking flag, and then the mechanism of scheduling callbacks with loop call soon, calling this under step, is what makes the coroutine advance one step at each iteration until it reaches the end, and this task is finished doing its work. So that's actually all I got for you guys today. There's a lot more in asyncio. I just scratched the under of the hood surface. I hope you learned something. I would recommend you to learn that PEP is actually a very good read. Documentation is also very good. Don't be afraid of looking inside, because when you open all those files, there's a lot of abstractions and stuff, but there's a lot of things to be learned. And join the mailing list. It's very friendly people there to answer all your questions. And that's all I got. If you have any questions, feel free to ask or reach out to me. That's my website, my Twitter handle. I'm very happy to answer any questions you may have. Thank you.
Thank you. Very good talk.
Thank you. It basically ends up being the same, in the sense that, well, not the task on its own right, but the whole mechanism of using yield from to wait for a callback, doing the uncallback way, let's say, that is the same idea as the inline callbacks, or in a way like greenlet. In greenlet, you also use sort of a similar idiom. You take the current greenlet, and then you yield somewhere else, and when the result comes back, you switch back to this one and continue with what you were doing. So this is a similar approach, but with explicit yielding points, let's say, or which is where you see yield from, that's when things are happening. Any other questions? Yep.
So with asyncio, you don't spawn new thread to do something, so you don't have to jail constantly context switch?
The GIL is always there. One important thing to note is that asyncio is built for I/O, as the name says. And every I/O function relinquishes the GIL. So don't be confused by the fact that there is a GIL. If you run 10 threads for 10 sockets, they will cooperate. Because when the socket module internally, if you look inside, you will see that when it calls the underlying socket function, let's say connect, when you want to actually connect, that function is surrounded by PyAllow threads, which basically means get off the GIL, and when this function returns, I will get the GIL again. But in the meanwhile, do something else. So if you're doing I/O with multiple threads at the same time, you're fine. Now, there's still a chance that you use multiple threads in asyncio. The event loop has an API, an executor API. This API uses the executor from concurrent.futures package to, for example, run a blocking call in a thread pool. So if it's an I/O function, you can run it in a thread and wait for the result. And because of what I said about the GIL, this is good. This is actually used internally even to do get ADDR info. So to resolve a domain name to an IPv4, IPv6 address, this is done in a blocking way, but it's offloaded to a thread. And then we use a future and a wrap future thing to wait for it. So this idiom we talked about. Now, if you're doing a CPU-bound task, let's say you're doing the Fibonacci thing, you can't do it in a thread because of the GIL. It's a CPU-bound, so that will not yield the GIL. Now, how you can do this is you can use a different type of executor. You can use a process pool executor, which will run your function in a different process and then give you back the result. And this will not block you at all. I hope that answered the question. Any other question? Yeah?
So it seems like this is using generator functions to create coroutines in Python, because Python doesn't really have real coroutines.
It actually does. The .send and .throw, at that point, the generators became coroutines.
Well, kind of. I would say, so stackless has real coroutines, and it has channels for sending data back and forth between
Yes.
coroutines. And my question is, if asyncio was designed for stackless Python, would it look very different, or would it look almost the same?
Well, I think it would look different because actually, I'm not sure if you were at the G-Event talk this morning, but basically, this is the explicit versus implicit kind of thing. So in Python, these coroutines have a limitation, let's say, that you can only go back to, you only go back one level, right? So you can't say you're 3 levels deep and you can't go from here all the way to the top. So in that sense, they are more limited. However, to be honest,
To solve that is you have each one calling yield from, yield from, yield from, so each one is a generator.
exactly. So each one is a generator of itself. Now, this has some advantages and, well, some. For me, to be honest, I'm still undecided what is the best looking or the best model. I'm trying to figure it out. And for one thing, being explicit is kind of helpful because when you see yield from somewhere, you know exactly at what point in the function that can go and do something else. If you're looking at a piece of monkey-patched code, you cannot be 100% sure what of those function calls will actually switch away. And then you would need to let's say that the execution process is not that predictable unless you know all the code. If you wrote all the code, you know what switches, what doesn't switch. But even if you didn't write the code, you just need to look at where yield from appears. If it's there, it means that piece of code goes and waits. Otherwise, it doesn't. It's synchronous, and that's it. So, trade-offs and choices, life. Anything else? All right. I'll be around. If any other question arises, find me or hit me up online. Thank you so much.